There are a lot of streams and rivers that come through Newark, New Jersey, and all over the area. In fact, all over the United States there's streams and rivers, okay? And they're important things as far as bringing water in and taking other things out of the area. And so streams are one of these things that we have to keep an eye on. So what we're going to do today then is to look at a couple of different things, 3 different things. 1, we're going to make a gauging station. 2, we're going to look at the processes of a meandering stream. And 3, we're going to do a dam burst. So the first thing we can talk about with the gauging station is how they're put together. And basically there is a height of water, and there's a little house there, and the house basically sits beside the river. The water can feed into the house or back out into the river, and there's floats inside of this house, and they keep track of how high the water is in the stream and in the base of the house. Now there's a couple of parts of where the water sits in the stream bed. And the first thing is that you have what is called bank height. And so if it's right up to the top of the bank, that's bank full of stream for how much water is in the stream bed. If it's below that, then it's below the bank full. If it gets above that, that's what we call flood stage. So those are the 3 stages that you have. Now, what we do basically is you measure that height. And what we're going to do in one of the exercises is to show you how to measure the height and see what it means. Okay, so they might say, well, it's 10 feet above flood stage. Well, what does 10 feet mean? If that's a river that's 30 feet deep or something like that, is 10 feet a lot? Well, what we're going to see is that once the river goes above flood stage and spreads out over an area, it represents a huge amount of water coming through. And that's measured in what we call discharge. Okay, so we're going to look at the discharge of a river based on how much water is going through. When it goes above, it floods, okay? And flooding gets all over the sides, and it costs us a huge amount of money. It's probably one of the biggest expenses in the world that we have to face from a natural sources is flooding, okay? And so flooding, basically, if it's a river or a stream, is going to cost us a lot of money. So it's very important that we keep track of what our flood stage is and how much water is in it. Okay, so the first thing you're going to do is you're going to build your own gauging station. And what we have down here in this straightaway part of the table is you can see there's 3 different levels. And what we're going to do is we're going to start off at the first level, and you're going to see how fast is this water flowing. So you take a little bead, and you can see that there's a ruler along the one side. You take the stopwatch, put the bead into the water, press the stopwatch to start, stop it when it gets to the end, and now you have a distance read off of your ruler, a time read off of your stopwatch, and that will give you the speed. You look at the cross-sectional area of how much this stream is flowing through, multiplied by the velocity that you just calculated, and that will give you discharge. Now what we're going to do is we're going to repeat this for each of the heights. We're going to go on to the next height and then finally the top height and see how much discharge comes for every little bit of height change that we get on our stream. And you're going to plot this up, and then you're going to make your own gauging station. Now the next thing we're going to do is we're going to take a look at a different type of streams. And there's a bunch of types depending on what the topography is like. So in areas with steep hills, you get fast flowing water, and the streams are relatively straight. Okay, and typically what we have in those are what are called braided streams. Okay, and those are straight, fast flowing streams, something like the Colorado River. But if a stream flows on a flat area, it will tend to wind around and become what is called a meander belt. Okay? And with these meander belts, they can constantly be shifting their channels from side to side. And the reason for this is the velocity is different depending where you are in the stream. Now what we're going to do is look at some of the background on meander belts, and then we're going to talk about how that goes into a exercise that you're going to do today. Okay, so the first thing I want to talk about is a little diagram called the Hjulström diagram. Now you don't have to know all the details of the Hjulström diagram, but the Hjulström diagram basically kind of separates things into 2 main areas. Either you deposit sediment or you erode sediment. So if sediment can be carried along, just like muddy water, that means if it's muddy and moving, brown rivers, that means it's carrying a lot of sediment. If you have rivers that are clear, it means they're not carrying a lot of sediment. And so fast-flowing water tends to carry sediment. Slow-flowing water tends to deposit it. Okay, and so that's our simple relation we're going to look at. This graph kind of tells us the faster it flows, the bigger things it can carry. That's about the only difference that this diagram shows us. Okay, so basically what we're going to look at then is we're going to look at the parts of a meander belt. Okay, and there's two basic ideas on this. In the meander belt, starting with their windy shaped channels. And with that windy shape comes a little problem. And the problem is that water wants to flow straight. It does not want to curve. And so therefore, if you're going to try to flow water straight, then it's going to necessarily bang against the outside of a bank and not on the inside. Okay, so when you have a curve in the river, the water is going to try to flow straight and goes to the outside of the curve and pushes against it. That's where the fast part of the water flows. Okay, and that we call the cut bank. Okay, so the cut bank is what the water is banging into. It tends to erode away that bank, and you get almost like a cliff against it. That's the cut bank. On the inside of the loop, the water is flowing much slower. And so therefore, that is where you get the point bar. Okay, and that deposits new sediment all along. So if you look at this, you can see where the main channel is going, where the main flow is going, and you can see that it's banging against the outside of these loops and not on the inside. Okay, and this banging causes the river to shift. The channel is constantly shifting. It's pushing out against the outer part of the loop, and it's letting the inside of the loop grow in size. Okay, and so that's why you get that whip shape, that windy shape to these rivers. Okay, so we have the first part. As I said, we have one side is the cut bank and one side is the point bar. And here's a picture of a cut bank. So you can see it's almost got a cliff on one side. You can see that the tree is in the water. Okay, and that means that what happens is you're undermining that side of the river. So the bank is being undermined constantly, and the material, the soils, the rock, whatever else is in there, is falling into the river, and therefore you're able to grow in this direction. Now the problem is if you have anything sitting up on the side of the cut bank, as it cuts deeper and deeper into this edge, things are going to wind up falling in the river. So you can see that tree at one point was sitting up on the bank with its roots in the soil was cut away, and the tree fell into the river. And that's how you get the cut bank. Now, if you take a look at this picture, this is a long meandering stream that you can see. And the reason I picked this was because you can see it's got a lot of white sand in it. So look at those inside loops on the rivers, on the streams. You can see the point bar. The point bar is freshly deposited sand that's being put on the inside of the river. Notice it's only on that point bar side. Outside, it's cutting right into the woods. Okay, so you can see that the trees and the edges all being cut into by the river, whereas on the far side, on the inside part of the loop, you can see white sand being deposited. So right along here, you can see very clearly which is the point bar and which is the cut bank. Okay, now, the shifting channels that we have in here, as you can see, these things are constantly slowly moving, but at sometimes they will shift quickly. Okay, and what we have is a process called neck cutoff. Okay, and so there are actually two of them. One's called chute cutoff, but what we're going to look at today is neck cutoff. And as the two edges are cut into, their cut banks are being cut continuously by this moving river, sooner or later those two rounded edges start getting closer and closer together. Okay, and all of a sudden there's not much land in between the two loops of the river. Now what will happen is maybe it's a flood, maybe something just gives, or maybe some vegetation disappears, and bang, all of a sudden the stream, instead of going all the way around the loop, it cuts off. Okay, and now the stream is flowing straight between one edge of the loop and the other edge, and the whole big part of the loop gets cut off. And that is what is called an oxbow lake. So you have now created an oxbow lake by neck cutoff. Okay, so oxbow lakes come after you get cut off. They're separated from the main river, and the big thing about them is they have no flow in them. So they are actually lakes. Okay, and you can see in the pictures, you can go from step to step to step where the river will cut across, and all of a sudden it'll silt up, and you don't have any more, and it's completely cut off from the flowing water from the non-flowing water, and that's how you develop these. Okay, and so the next thing is that you can see these in pictures by the watercolor. Okay, the flowing rivers will have muddy water because they're constantly moving. And remember, we said that if you have flowing water, it can carry along sediment, and the sediment gives it kind of a brownish color. So you can see in this picture here, we have the brownish color in the flowing river. Now you also see those little rounded lakes in there, and they look like you can see that they once were a round part of the river, part of the meander, and now it's completely cut off. So the brown part is flowing, and the blue is now standing water. Okay, the upper part of this stream table is a meander belt. So this is the silver part. You can see this winding channel that runs through here, and this is what a meander belt would look like. Now what we're going to do in here is we're going to look at the velocity on the inside arc of one of these, in other words the point bar side, versus the outside arc on one of these loops. You'll notice that the red arrows are where you start and where you stop, and the same with the blue arrows on the inside. On the vertical walls on the loops, you can see that there are vertical lines, and these are centimeters apart. So you can count how many centimeters there are around as far as how far you're going to go. So the first thing we're going to do then is to try the outside. We take a bead and we drop it in and hit the stopwatch, and then see how fast that took to go around, and that'll give us our first velocity. Then the next thing we're going to do then is we are going to try the inside part of the loop. So we start where the arrow is on the blue arrow, and again we drop the bead in and stop it, and then we can calculate how fast the inner part of the loop goes as well. Okay, once you determine where you think the faster flow is and the slower flow is, then you can determine where you think it's going to deposit sand. And what we'll do then is we're going to take some sand and we're going to dribble it in the top part here and let the sand run around and deposit, and then see if you're right. See if you know where you were going to deposit sand as opposed to eroding, just based on which is faster and which is slower. Slower deposits, faster erodes. The next thing we're going to do is do a chute or a neck cutoff of this stream. And the way we're going to do that is to remove this little plug right here. And without the plug in place, you'll notice that the stream then flows directly through and not around the loop anymore. And so therefore we are creating a oxbow lake over here and a straight through down here. Again, if we dribble a little more sand in, you will see where the sand will then tend to go to help form that oxbow lake. So the oxbow lake will be done by cutting off the neck of this meander. Okay, the next thing we can do on these things is to consider what happens if we dam up a river. Okay, and so damming a river, basically it slows the water down behind it. Okay, so once you put a dam in, all the water can only go over the top of the dam. The whole bottom part of the dam slows down. Okay, so all the water behind the dam, except that which is flowing right over the top, is slowed down. And what happens is that because you're slowing it down, just like we know from that diagram, you're going to deposit sediment. So behind a dam, it tends to what we call silt up. You get a lot of sediment sitting behind the dam. Okay, and that can be a problem at some point because all that sediment usually is what feeds our beaches. So it keeps our beaches full of sand and provides sediment for other areas downstream from where the dam is, and all of a sudden it's not there anymore, and so you're going to get erosion of the stream bed. You're going to have beaches without enough sand in them. So that can be a problem. Even though the dam we make for a specific reason, we can get some problems from it. Okay, so the first thing is we get siltation behind the dam, just the same reason why we got sedimentation in a point bar. Now, what can happen with the other thing with these dams is they're constantly being eroded all over the top, around the sides. Put a little bit too much water in them, and what happens? You get what is called a dam burst. And dam bursts are very dangerous. Okay, when the dam lets go and lets a whole reservoir go from behind it, it can cause a huge amount of damage. We've had some really tremendous disasters from dam bursts in history.
Okay. The last thing we're going to do is we're going to plug up our system here and create a lake or a reservoir. Now in this case now we've cut off the downslope part of the stream, the straight part, and the back part in here, the meander part, is now filling up. If you dribble any sand in here now, you will see where it deposits. And you'll see that it's going to deposit pretty much everywhere because it's much slower. Now once we get this whole thing filled up, what you're going to do is decide how dangerous is it to live on the banks of a river. And so what you're going to do is make a little town down in the straight section of the stream and out of those monopoly houses. We're going to let this stream fill completely up and make a reservoir, and then what we're going to do is pop it and drop that flood down the stream and see what it does to your town. So you get to flood out the town and see how many people are survive.